A2 Further Maths, Modelling with Differential Equations. Okay, so hopefully by now you've done plenty of work at first order differential equations and second order differential equations. You can solve them either by using integrating factors, or you can solve them using complementary functions and particular integrals, and then going on and finding general solutions or particular solutions. Now all of that should have made sense to you, and you should be able to use those very efficiently with, like I said, both first order and second order differential equations by now. Because what's going to happen is potentially in your exams or further on in your questions, you're going to look at changing real life problems like the one in front of you into differential equations and then using those skills to solve them. Okay, so what we're going to do is we're going to look at two examples of how you can use real life problems and change them into differential equations. You've already seen some of these situations, of course, in normal maths. Right, all we're going to do is change them into differential equations that you have to use further math skills to solve. Okay, so let's have a quick read through this. What I would recommend you do is in your notebook is either copy down the question in full. Okay, you might think that's too much, so you might want to just cut it down and just put some key facts down. I don't mind, or you might want to print it off and stick it in your notebook. It really doesn't matter as long as you've got something to refer back to when you do your revision. So what we're going to do is I'm going to give you a chance to get that down in your notebook, have a read through it, have a go at it yourself. You might want to just try the whole thing yourself first, see if you can form the differential equation and solve it, or you might want to just wait while I go through the solution. It's up to you. But what I'm going to do is ask you to pause now, and then we'll get on in a second. Okay, so what we're going to do is the first thing we really need to do is just have a quick scan through it. You don't need to take anything down just yet, and just think about maybe what variables we're going to be doing. Doesn't matter if you have too many different variables or ones you don't use later on, as long as we've got everything covered. So I'll show you what I mean. The frozen pie has a temperature of minus 15 degrees Celsius. In other words, one of the variables is probably going to be the temperature of the pie itself. Okay, so the temperature of the pie, mentioned a few times, look, temperature of the pie is this, temperature of the pie is that. So the temperature of the pie is going to be a variable, something that's changing over time. Now, I don't want to keep writing temperature of the pie, so that one I'm going to definitely define as a variable. What else? Time, but time is already defined by lowercase t. That's okay. And temperature of the oven as well. Look, the oven is switched on so that its temperature, blah, 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 is that. Now, that is the temperature of the oven. So I'm going to need to define that as well. Okay, so what I'm going to do first of all is just define both the temperature of the pie as capital T for temperature, and the temperature of the oven, because I've already used capital T for temperature, the next one along is most likely theta for temperatures. Okay, we use it for angles and temperatures. So I'm using theta. So there we go. I've just defined both the temperature of both of those parts. Once I've done that, I can then just start either looking through the important facts one line at a time and seeing if we can change them to equations, or maybe I'll change them just to some important facts like the first line that I might end up using later on. So the first line says a frozen pie with a temperature of minus 15 degrees Celsius is placed in the oven. Now what it's saying there is that initially the frozen pie has a temperature of minus 15 degrees Celsius. So what I'm going to do is I'm just going to write that one down first of all, that when t equals 0, the temperature is minus 15 degrees Celsius. Now that's the temperature of the pie, so that's t equals. So there we go. When t equals 0, then capital T equals minus 15. I'm unlikely to use that straight away. I'm probably going to use that later on to find a particular solution, but I'm just making a note of it. Okay, so that's our first line done. What about the second line? The oven is switched on so that its temperature at time t minutes is given by 18 plus 10t. Now they're giving you an equation for the temperature of the oven. All right, there's nothing about rates of change over time or anything like that. They're telling you that you can work out the temperature of the oven by just putting T straight into that equation. So what we know is temperature of the oven, which I've called theta, equals 18 plus 10T. Okay, looking for the words things like change and stuff like that in there, that or increases at a rate, anything like those sorts of words means that you're talking about changing it to a d theta over dt. But it's not mentioned in there, so it's literally just writing theta equals 18 plus 10t. Right, so now we've got that part done. Let's have a read of this one. The temperature of the pie increases at a rate. So there we go. There's the key language that you're looking for. It's increasing at a rate. So in other words, it's changed its temperature over time. That makes sense. The temperature of the pie changes over time, and it's proportional to the difference between the temperature of the oven and the temperature of the pie. Now the difference, if you wanted to work out the difference between the temperature of two things, is by doing a subtraction. So we can rewrite this as the temperature of the pie, which is dt over dt, right? Changing the temperature over the change in the time, is proportional to the difference between the temperature of the oven and the temperature of the pie. Now clearly that's never going to be negative, right? Because the pie is only going to get as hot as the oven. It's not going to get hotter than the oven itself. Okay, so where we got that's where we got this sentence from. Now I don't like writing with proportional signs, so I know that you know how to change that. So you don't need to write that bit in. You can go straight to this if you want to, straight to the equation. So the change in temperature over the change in time is equal to some amount of the temperature of the oven minus the temperature of the pie. So I can write it in that sort of way. And there we go. I've got a differential equation right there. And that's pretty much the hard work done now. I've got the differential equation. What I need to do now is go about solving that equation. So how can I solve that equation? Well, I can certainly just make sure I put it all in the same terms. So I'm putting it in terms of lowercase t there and capital T. All right, so I've got just two. K is a constant, and I might be able to use that. Initially, the temperature is increasing at a rate of 0.33 degrees Celsius per minute. So there's some extra hints in here to help me work out that K value, because it's giving me the increased rates. So let's make use of that first of all, initially. So that means T equals naught, time equals naught. The temperature of the pie, which is our capital T value, has got a rate, which is that, of 0.33 degrees Celsius. So I know, using that bit of information just there, that I should be able to go on and hopefully work out what the K value is. Because don't also forget that when T equals naught, the initial pi's temperature was minus 15. So I can put all that information into our differential equation. All right, so I put that in. I can put the 0.3 equals K lots of to get my constant, get my K value. All right, so those two lines are what I'm using there. When T equals naught, I've got a temperature and I've got a rate of change. So I get a K value of 0.01. So what I can do now is forget all the other information. Let's just get our differential equation just there and our K value just here and put those together. All right, I've done all the hard work now. So I'll put those together and it leads to my differential equation of D temperature, change in temperature over change in time equals 0.1 lots of 18 plus 10t minus t. And I can say I've got my differential equation ready to work out now because I've only got two variables in it, temperature, the pi, and time. Right, so let's get rid of those two bits and let's rearrange our differential equation. Now at this point you could have two options. You could divide everything by 100 and then use an integrating factor. That's one option. Or you could use a a complementary function and a particular integral and solve it that way. It's up to you, okay? Because you've got a first order, you can solve it either way around you like. Now I'm opting in this case by doing a particular integral and a complementary function. So the first bit, the complementary function or complementary equation, can be worked out by just setting it equal to 0. Now if it's equal to 0, then I can just rearrange and I'm trying to just separate out the variables. So I've got 1 over capital T equals minus 100. I'm sure you can rearrange and see where that comes from. And you might want to pause here and just finish it off yourself anyway. So once I've got that, I can integrate both sides in terms of time, so dt. So I get that. And then once I've got that part, I can then solve those two integrals. So when I solve these two integrals, you're just going to get a ln. Be careful not to write something silly like ln 100. Of course, that is just a number, so that's going to be minus 1 over 100t plus our constant of integration. So there we go. I've got my complementary equation. Ideally, I want t equals. Okay, so capital T equals, because I'm trying to work out the temperature of the pi. I'm trying to get the equation for the temperature of the pi. So I can use the exponential function on both sides. And so I can rearrange it to that. Just be very careful, making sure you understand how to get from that to that. We can see that it's going to be e of all of that, and then e to the power c is where the a part comes from, because e to the power c is just a number. By now, you should have seen that so many times that you should fully understand where do you get this part from. Okay, if you don't, then you need to go back, you need to have a look, and you need to be asking. Right, so we got down to there. There's our complementary equation ticked off. Let's leave that on there, and let's just go back and have a look at the particular integral. Now, particular integral, I'm looking at this side now. So the 18 plus 10t. What can I stick in for t on this side that comes out as 18 plus 10t? Now, I can see that's like a linear equation. So my first thought is it should be some type of linear equation that I'm going to substitute in. Because if that's a linear equation, that one will also be some sort of linear function. So there we go. When t equals a plus bt, because that's where this equation is going to come from, dt over dt equals b. So that's easy enough, just differentiated that. And now I can substitute all that in. And then I can compare some coefficients and hopefully work out what the a and the b value is going to be. So yes, 100b plus a plus bt equals 18 plus 10t. I'm fairly confident you could do this yourself. Okay, we can see that b has to be 10, because that's the only coefficient for t. So b has to equal 10, and that would lead to a equaling minus 982. So that is my particular integral there of 10t minus 982. Now I can put both of those two things together now then to get my general solution. So my general solution is going to be the temperature of the pi is equal to the complementary equation, the complementary function, plus 10t minus 982. Okay, and you could check that. You could substitute that back in, and hopefully you'd get exactly the same answer. And you should do. Okay, because this part's just going to get you 0, and this part is going to get you the 18 plus 10t. Right, so now we've got the general solution. Have we finished the question? Not quite. Find the temperature of the pi when it's been in the oven for 20 minutes. So this last section just here involves us trying to work out what the temperatures of the pi is going to be in 20 minutes. Now the problem with that, of course, is that I don't have the a value. I still have an unknown constant in there. So I'm going to have to work that out. Now I can go back and I can reuse previous information. There's nothing wrong with going back and using when t equals 0, temperature of the pi equals minus 15. So I can reuse this bit of information. I used it earlier on to work out the other constant. I'm going to use it again to work out this a constant just here. So I'll substitute it all in. You could do the number crunching if you want to, or you can just cheat and copy mine. There's 967 as my a value, and therefore I've now got a particular solution. All right, so a particular solution for the temperature of the pi. Right, and that's it. All right, if I ever want to work out the temperature of the pi now for whatever time, I could just put the time into that equation, and it would give me the temperature of the pi. I want it for a certain time. I want it for 20 minutes. Just be very careful the examiner doesn't try to chicken you out. It's minutes there, and this is in terms of minutes. That's good. So I can put my 20 in. So when t equals 20, the temperature of the pi is, with those two subbed in, out comes 9.71 degrees Celsius. So in 20 minutes, it hasn't heated up that much, but it will start getting a lot hotter very quickly. Okay. Right, make sure you've got down what you need before you move on. Pause if you need to. Okay, speaking of which, if you did want to get to the correct temperatures to be eaten, They're expecting you to get to 165. So after 20 minutes is only about roughly 10 degrees Celsius. So we want to get, sorry, not degrees Fahrenheit, degrees Celsius. We want to get to about 74. What I'd like you to do is just see if you can work to the nearest minute how long it should cook the pie. Nothing to do with differential equations, but it is a sort of, A star question they might ask at the end, which crosses over other topics. Could you now use your equation to see if you can work out that? So I want to pause there, have a go at that yourself. Okay, so there's your equation that you're trying to use. So if you didn't even know that bit, you might want to pause again and have another go. How could you go about solving that equation is what I'd ask. Okay, so you're trying to solve that equation. If you try to rearrange it, you're going to get yourself in a right pickle. But don't forget, you've got other techniques. All right, you've got other techniques that you can use to potentially solve, sort of equations like that, which are not very easy to rearrange. And the other techniques you could use, one of them, of course, is using your calculator. Your calculator has a button that allows you to work out solutions to equations like that. Okay. The other option would be potentially using an iterative method. There's nothing wrong with you using an iterative method. That's what they're there for. The iterative method is for solving equations like this. So I know this is normal math skills, but it doesn't do any harm. That could still cross over into your further maths. So just see if you can find a solution if the initial time was 20 minutes. So we're building on from our initial 20 minutes. So what would be the temperature of the pie after 20 minutes? Okay, so hopefully you know how to do the iterative method. If you don't, you definitely need to go back over the iterative method lesson and figure out how to do it and remember how to do it. So the first thing we need to do is rewrite it as a t equals equation. Now I can do that by maybe taking the plus 10t to this side, okay, or in fact taking everything to that side apart from the 10t and then dividing by 10. If I do that, then what I can get is I can get an iterative formula like this. I can substitute in my value, so when t0 equals 20, and then once I've done that, I can work out the solution. So there we go, t equals approximately 42 minutes. You want to leave your frozen pie in for about 42 minutes. Okay, so let's look at a second question then. And again, same as before, if you want to just pause there, write down any key facts, maybe have a go at it yourself, okay, however you feel, and we'll have a look through how to solve this one using a slightly different technique. Okay, so hopefully you've got down the information and you've maybe had a go yourself. Let's have a look and just see. So last time we talked about just writing down the variables. Now in this case, I think most of the variables are defined. Let's have a quick look. We've got town population. Okay, so we've got a town population just there. So that's an increase in the town population of the town, moved away from the town, so that's population of the town. So most of the variables are already defined. T is defined. So we've really only got two things to consider in this question. The population of the town and the T value. Now you might have had the increase and decrease of the population of the town. But again, what you'll find is that those two disappear or you're not used at all. So it doesn't matter if you have extra variables that you end up not using. So I'm going to just go with, first of all, looking at the rate of change of this town. So that's what it's all about. This town's population is changing. Now the change in the population is doing two things. The size of the size of the town is changing and increasing at a rate of 0.02y. Okay, so it has a natural rate of growth. Okay, so that's the first thing. So if I had just that on its own, I could say quite comfortably then that the change in the y value over the change in the time is equal to 0.02y. That's how it's changing over time. In 2020, the population was 25,000, so that's probably a bit of information to help me work out some constants later. So you could write that down if you want to. Taking t as the time in years from 2020. So 2020 is your initial starting point. That's when t equals 0. So I've got 250,000 as my starting value. What else have I got? I've also got this bit just here. Over the next few years, people move away from the town. So that's a decrease of 0.4 plus 0.9 e to the 0.2t. So they are decreasing at this rate. So we've got an increase in the rate of change of the population and then the decrease just here. So what I want to do is just tie those two bits of information together. So I know that the rate of change of my town's population over time is equal to 0.02y minus what's going away from the town, which is 0.4 plus 0.9 e to 0.2t. Just be very wary about making a silly negative sign error on that. So there we go. I've got my equation all set up, my differential equation. And in fact, that looks pretty much done because you've got it in terms of both t and y. So this one is a little bit different to the previous one in that I don't have to start figuring out other little bits and bobs and other constants. It's pretty much set straight away, although it does seem a bit more messy with some of the numbers. So what I'm going to do is just rearrange that slightly, okay, by maybe taking that over to that side and then just separating out the minus. I don't blame you for trying to rearrange it and get rid of all these negatives, but I've left it like that on purpose because what I'm going to do with this one is solve it using an integrating factor. I've noticed that I could write the equation as dy over dt minus some function of y equals some function of t over this side. And so because I can write it in that way, I could solve it using an integrating factor. Okay, so the integrating factor we're going to use, you need to learn this off by heart on how to find it, is going to be e to the power of the integral of minus 0.02. Okay, so that's how we work out our integrating factor. Once we've got dy over dt, we've got this part just here, so it's e to the power of the integral of minus 0.02. And then once I multiply through by whatever this answer is, then that allows me to use product rule in reverse. So I've got e to the minus 0.02t, and that is my integrating factor right there. So what I can do now is multiply through by that integrating factor. So I can do that. And then what I've noticed is that this side is just the product rule. All right, the integral times that one left alone, that one differentiated, minus that one differentiated, and that one left alone. Okay, so it's just going to be the product rule, which makes it very easy to solve then, because I'm just solving or just differentiating the integrating factor times y. And on this side, I can do whatever the integrating factor is. There it is. Expand on those brackets. Now I'm going to neaten this side up slightly. Right, but notice that you've already passed all the words. You've solved your differential equation and now you're doing the same skills that you've practiced over and over again with those previous differential equations. This is why I said to you, you had to be absolutely solid at solving those differential equations for the sort of big markers like this. Okay, so can I carry on working with this? Yes, this bit is just going to be the IY, because that's going to cancel out. So that's okay, we can just do that. And then this side is the integration of that part. So what do I get then? Well, if I put those together, work them out, I'm going to get this answer. So that bit cancels with the differentiation. So therefore we've got just e to the minus 0.02t times y. And on this side, you're just integrating these two. So go careful not to make a silly mistake. But you've got those two integrated with that. Plus c. Of course, you can't put these two together at all. They're not the same powers. Right, so once I've done that, I've solved it. I could do a bit of rearranging, maybe divide through by e to the minus 0.02t. And then once I've done that, that should tell me what y equals. So I get this answer. All right, so 20 minus, and notice on this part, the c value just stays at the front, and I've changed that to a minus. This bit here, I've added it on, so that's where that bit comes from. So it ends up as a relatively neat equation, but there's a general solution right there because I don't know what the constant is. Do I need to work out the constant? Yes, because I'm looking for write down the first order differential equation and you make use of it to predict the population. So I need a particular integral. So I might just have a look and see, is there anything I haven't used yet? Well, I haven't made use of this initial population just here. So because I haven't used the initial population, that's going to help me work out this bit. So I've got when t equals 0, y equals 250. So I'm doing it per 1,000 of people. Okay, so there's 1,000 people per year. Right, so you've got 250. You don't have to. You could stick with that number just there. That would get you the same answer. So 250 substituted into there gets you to those values just then. Gets me a C value of 235. So I can substitute that back in, and there is my particular solution for the town's population right there. Once I've done that, what I can do now is I can work out the answer to this bit. Predict the population at the end of 2020, so nearest 1,000. So I could use my model to do that. It works it out to the nearest 1,000. So in 2025, that's going to be 5 years on from 2020. So I'm putting in t equals 5, and I can substitute that into my equation, and that's going to tell me what y value is. Okay, so a relatively straightforward end to that equation. So there we go, 266, which of course is a population of 266,000. Now, if you didn't change it to per 1,000, right? Some of you might notice it's thousands there, but you might have naturally just put in 250,000. It's worth just checking that and seeing whether you would have got the same answer. Right? Would it have really made any difference of changing it or not changing it? Okay, I just want you to be wary about the different units. So when these were talking about per 1,000, you might have thought, okay, that one is 250,000. Okay, but did it make any difference? Have a go and see what you think. Right, so there's two examples. Now, the problem with these questions is the examiners could ask you any type of questions in the real world, and you've got to use these skills of being able to form the differential equations. Now, what you may find is that the examiners knows that if people find it difficult to form the differential equations, and they will give you the differential equation to solve as well. So don't start reading one and just quit too early, because what you might find is that actually the formula of the equation is quite difficult, but the solving it is just my normal skills that I'm going through and practiced a lot. Okay, so always look out for, has the examiner given me the differential equation, so therefore I can definitely get the bulk of the marks even if I can't figure out how to form it. But what I would like you to do, please, is I would like you to have a go at that full exercise, and I would like you to take your time trying to form the differential equations for each of those.